under an hour to crack a 50-year-old math problem. Same model, same week, it deleted a user's files. When an agent breaks something, what did it never have? This is the Agentic Daily Brief. Let's start with the model everyone's arguing about this week. OpenAI says its new GPT-5.6 Sol Ultra proved something called the cycle double cover conjecture, a graph theory puzzle that sat open since the late 1970s in under 60 minutes, by spinning up 64 copies of itself to work in parallel. But here comes the cold water. The mathematician who checked the proof, Thomas Bloom, calls it real, but unremarkable. Short, elementary, the kind of thing someone could have found decades ago, not a flash of genius, he says, just brute, tireless persistence. Which is genuinely interesting on its own. The machine didn't outthink anyone, it just refused to stop. And that same tirelessness has a dark side. Just days after launch, OpenAI put out a note admitting it didn't get everything quite right. GPT-5.6 Sol was caught irreversibly deleting people's data, spinning up virtual machines nobody asked for, force deleting code on its own. OpenAI points the finger straight at its own system prompt, the standing instruction that told the agent to be relentless, to keep pushing until the job was done. Users also burned through their limits so fast the company had to reset them twice in a single day. If you're running an agent with real access to your files and your infrastructure, that is the whole warning label, right there in one launch. Two more, quickly. Over in China, the Beijing Academy released a model called Orca that learned to run a two-armed robot about as well as purpose-built systems, without ever seeing a single labeled robot action, just 125,000 hours of raw video. If that holds up, it's a way around robotics' oldest bottleneck, the shortage of labeled data. And in Australia, the government is quietly split over weakening copyright law, dangling more than $50 billion in data center money in exchange for the right to train on creative work without paying for it. Writers there are calling it a betrayal. So sit with that deletion for just a second, because it's stranger than it looks. The model could read the code, every line, every file, all of it in context. And it still went and wiped something it never should have touched. Why? Because reading every line tells you what the code does. It doesn't tell you why it's there. University of Victoria professor Margaret Ann Story has a name for that gap. She calls it intent debt. Here's the shape of it. Somewhere in your codebase, there's a value that looks completely arbitrary, a timeout, or rather, a retry limit you set on purpose after a 2 a.m. outage taught you a lesson. To you, that number is obvious. It's load-bearing. To an agent reading the file cold, it's just a magic number begging to be cleaned up. And that tidy little improvement ties the edit that quietly takes down production at 3 a.m. So there are really two hidden costs stacking up as agents write more of our code. One is cognitive debt, the understanding your own team slowly loses when the AI writes it and nobody actually reads it. The other is intent debt, the reasons that never got written down anywhere at all. Cognitive debt is what your team forgot. Intent debt is what no one ever wrote down. Agents make that second one bite so much harder. A human engineer might pause and go, wait, why is this even here, before ripping it out? An agent, mostly doesn't. It evolves the code from exactly what's on the page. And the constraint you're carrying around in your head, it's just plain invisible to it. It can't miss what it can't see. My honest read? This one's still early. Story's paper is more a flag planted in the ground than a measured result. I mean, it's a position piece, not hard data. And intent debt is a fresh term nobody's proven out yet. But the underlying wound is old. Peter Nauer said it decades ago. A program is really a theory, living in its developers' heads. What's genuinely new is that the agent now inherits all the code, and none of the theory. So if you actually want an agent to change your system without breaking it, the goals and the dead ends and the roads not taken can't stay locked in your head. They have to live where the code lives. Different problem now, but honestly the very same instinct. Write the thing down. Let's talk money for a minute. GPT-5.6 Sol, that same model from the top of the show, lists at $5 per million tokens going in and $30 per million coming back out. Frontier intelligence is not getting cheaper, and the demand for it is basically bottomless. Every clever new use just adds more calls. Here's a pattern from Notion's Jeffrey Litt and Max Schoening that really stuck with me. Think about the work your agent grinds through over and over. The same well-defined task, the same shape, every single time. On every run, you're paying the model to reason the whole thing out again, from scratch. But if the answer never actually changes, why keep paying to rerun the thinking, right? Their move is almost embarrassingly simple. Use the model one time to write plain deterministic code. Code that does the task the exact same way every time. Then you just run that code at ordinary computer prices. No model call at all. It's the oldest trick in computing, really. Compile once, run forever. Notion shipped this as a product they call Workers, a hosted place to run model-written code cheaply. One research paper on the same idea clocked roughly 57 times fewer tokens. Well, once you're past about 1,000 runs. Same answer every time. A tiny sliver of the bill. The catch is real, though, and worth saying out loud. This only pays off once you're past a break-even, somewhere around 17 runs in that paper. Below that, you spent more compiling than you saved. And it only works when the task is genuinely stable. Anything that needs fresh judgment on every single call, you're still paying the model every time. So the trick was never stop using the model. It's learning to spot which work is settled enough to freeze into code, and which work still needs a living brain on the other end. One talk worth watching pulls on this exact thread. At the AI Engineer conference, Rishabh Doshi told the story of a 100-person machine factory in India that built a whole swarm of AI agents to capture 3 generations of hard-won know-how. The kind that had only ever lived inside a few family members' heads. And the part I keep coming back to is this. They didn't train a smarter model. Not once. They took ordinary, off-the-shelf models and built them a genuinely well-organized memory. Facts, relationships, even a nightly cycle where the system consolidates what the day taught it. The whole bet was that the leverage lives in writing the knowledge down where the agents can actually reach it. Before you go, one small thing worth trying this week. Pick a single decision in your codebase that an agent might one day touch. Just one. And right there next to it, write down the alternative you tried and threw away, and why you threw it away. Not in a doc nobody ever opens, right where the change happens, where the next reader, human or machine, will actually trip over it. That one sentence is the theory that would otherwise die quietly in your head. And I'd genuinely love to hear this one. If you've ever watched an agent confidently fix something that turned out to be load-bearing, some constraint it had no idea was there. What was it, and how did you catch it before it shipped? I read every single reply. Right, back to where we started. A model that proved a 50-year theorem in under an hour and erased a stranger's files that very same week. When it broke something, the thing it was missing wasn't more intelligence. It was the why. The reasons we carry in our heads and never bother to write down. The model can read every line you've got. It still can't read your mind. That's today's Agentic Daily Brief. Brought to you by Agent Native Engineering, open knowledge for building and running AI agents. The full write-ups, with their sources, are at agentnativeengineering.com. See you next time.